Hello there! Our lesson for today is limits and continuity. But before we proceed, please don't forget to subscribe. This is the definition of the limit of a function at a. So we have this equation. The limit of f of x as x approaches a is equal to L. The condition is, for every epsilon greater than 0, however small, there exists a delta greater than 0, such that the absolute value of f of x minus L is less than epsilon whenever the absolute value of x minus a is less than delta. What do we mean by this? We are just simply talking about distances. Remember, when we subtract numbers in the one-dimensional coordinate system, for example, 5 minus 3, the absolute value of 5 minus 3, or 3 minus 5, then we're just simply taking the distance or measuring the distance from 3 and 5, which is equal to 2. In the same principle, this is just simply the distance from f of x and L and the distance from x and a. Take a look at the illustration below. If this is a, and we're going to approach a here, so x approaches a means we approach a from the right and the left of a. For example, when x is somewhere here at distance delta from a, so you have a and a plus delta, your f of x lies somewhere here at this value. And as you move closer, take a look at how f behaves, f of x. Value of f of x also gets closer and closer to L. So that means to say that when this value becomes very small, the distance between x and a becomes very small, your f of x and L as well, their distances becomes very small. And that should be true as well for the left. As x approaches a from the left, if x is somewhere here, here the value of f of x is somewhere here, and as you move closer to a, x moves closer to a, f of x also moves closer and closer to L. So that is what we mean by this. Take a look at the following example. You have the limit of x squared minus 9 over x minus 3, which is equal to 6. Why? Because as we approach 3, meaning x approaches to 3 from both the right and the left, we have f of x is going to 6. Okay, as you move here, your f of x there approaches 6. And as well as you move x from the right of 3 going to 3, as we move closer, it also moves closer to this value 6. The graph of this function is just a line, x plus 3, without the hollow, without this 0.36, because this is undefined at x equals 3. Now you may also observe that the limit as we approach 3 from the right and from the left are the same. So they're going to the same value, 6. Actually, later on our discussion, we're going to discuss one-sided limits. We have the left side limit and the right hand side limit. Okay, and if those two limits both exist, then our limit exists as x approaches a certain number a. Okay, if these two does not coincide, as we can see in the next example, then the limit does not exist. Take a look at this example. We have a piecewise function. F of x is equal to x plus 3 if x is less than or equal to 2, and f of x is equal to x if x is greater than 2. Let us evaluate the limit of this function f of x as x approaches 2. So if we approach 2 from the right, what will happen is f of x behaves in this manner. It also approaches the number 2. While as you approach x from the left, your f of x approaches 5. This is the case where the limit of the function does not exist. Another condition that the limit of a function might not exist is when you have this. As x approaches 1, so what is the limit of this function as x approaches 1? You have this one is an asymptote. So from the right, you get to positive infinity. This goes up with no bound without touching the asymptote. And this one here on the left is moving downwards without touching x equals 1. So the limit here does not exist. Actually, if this curve here at the bottom is here, goes up as well, the same as on the right, then we might write the limit of f of x is equal to positive infinity. Or if this guy here is here at the bottom approaching as well to this asymptote, then we say that the limit of the function as x approaches 1 is negative infinity. But the two cases, positive infinity and negative infinity, we also say the limit of f of x there is or does not exist, though we may describe it as positive infinity and negative infinity. It also doesn't exist. You can also write it as it does not exist because it is not a number. Infinity and negative infinity is not a real number. Now these are the theorems that you use to evaluate limits. Number 1, the limit of f of x as x approaches a must be unique. As you can see, if the limit of f of x as x approaches a is L1 and L2, then these two must be equal. Limit of a function is unique. Number 2, if b and c are constants, then the limit of a linear function is equal to be a plus c. We just substitute the value a here. Actually, it could be, you can find out later that whenever you substitute a in your function and the function is defined, then that is your limit. Number 3, if c is a constant, then the limit of a constant is just the constant itself. And here, for any real number, the limit of x is equal to a. Just like what I said in number 2, when you substitute and you find out that the result is defined, or you got a real number, then that is the answer. Number 5, the limit of a sum is just the sum of the limits. Number 6, the limit of the product is just the product of the limits. Number 7, if you have n as a positive integer, then the limit of f of x raised to n would just be equal to the quantity of the limit of f of x raised to n. As you can see, if this is the case, limit can penetrate the power here. Okay? And for number 8, similarly, if you have the limit of f of x here, or the limit of the nth root of x, you have a radical with index n, is just equal to the nth root of the limit of f of x as x approaches a. The limit penetrates the radical, and it becomes a radicand here, provided that this radicand limit of f of x as x approaches a must exist as well. Number 9, the limit of a quotient is just the quotient of the limits, provided that the limit of the denominator is non-zero. So limit of f of x over g of x is just the limit of f of x over the limit of g of x when this limit of g of x is non-zero. If f of x is, or if the limit of the denominator here is 0, then you have to see two cases. Number 1, if the limit of f of x as well is 0, then all you need to do is remove the factors x minus a, because those factors are making your denominator and your numerator to be 0, and the resulting value will be the answer for your limit. And that is supported by theorem number 10, because if you have two functions f of x and g of x, they only differ in one factor, and that is x minus a. So for example, f of x contains x minus a, while the other one does not. then their limit are the same. Okay, so that is supporting this, the one that I mentioned. If you have a zero denominator here and a zero numerator limit, then you just simply cancel the factors that makes them zero, and if the resulting value is now a real number, then that is your answer. However, if this is 0 here, the limit of the denominator is 0, while the limit of the numerator is non-zero, then your limit there does not exist. And actually, we have a section for that. We call it infinite limits, because the answers to those problems are either positive infinity or negative infinity. Example. Actually, these are the exercises in your lecture slides. So example, you have the limit of x squared plus 2x plus 1 over x squared plus 4. Immediately take a look at the limit of the denominator. The limit of the denominator is 5, which is non-zero, so you just simply substitute 1 to x and you get 4 over 5. In your lecture slides, this is -1. So if that is the case, we still have a non-zero denominator while the numerator becomes 0. So 0 over non-zero, the answer is 0. Example number 2. You have the limit of the square root of x plus 2 minus 2 over x minus 2. As you substitute 2 here, as you evaluate the limit of the numerator and denominator, you will observe that both are 0. So proceed to removing the factors that makes the numerator and denominator 0. However, the one on top, it is not very obvious to factor out x minus 2 here. That is why we use a technique which is multiplying a conjugate for this numerator here, so that you can factor or you can find x minus 2. So multiply by the conjugate of this. We learned that in our rationalizing of denominator lesson. So a square root of x plus 2, you multiply it there both to numerator and denominator. So this guy will be squared and squared, so you have x plus 2 minus 4, which is x minus 2. You can cancel that with the denominator, leaving you with the limit of 1 over square root of x plus 2 plus 2, and now the denominator is non-zero, so just substitute and you get the limit of our function is actually 1/4. For the next example, you have the limit as x approaches 2 again of the cube root of the fraction x cubed minus 8 over x minus 2. Notice that it is a fraction whose limits of the denominator is also 0 and on top is 0. But this is easy to solve if you can remember your factoring. Well, we can put limits inside here, the cube root, but I just chose not to. That is still okay, or you may choose to put limits inside. Okay, but I chose to simplify x cubed minus 8 immediately using factoring skills or factoring techniques. This is the factor of x cubed minus 8, revealing x minus 2 here, and you can cancel x minus 2, so you get the limit of the cube root of x squared plus 2x plus 4. Then you just simply substitute. This is, you get a cube root of 12, and that is your answer. The next example is the limit of 1 over x times the quantity 1 over h plus x minus 1 over h. If you look clearly, if you observe clearly, as you substitute x to this, you have 0. And if you substitute x here inside, you've got 0 as well here. 0. This is 1 over h minus 1 over h is 0. So this is a case where you have a 0 over 0. Hence, the one that gives us a 0 over 0 here is the factor x. We need to find a factor x in the numerator to be able to cancel this x here. And to do that, we take the LCD of this fraction here. That's it. And then simplify, divide, multiply, divide by h, and multiply. So this is the case. H minus h is just 0, so you get a negative x here. You can cancel x, leaving a negative 1 over h times h plus x. As you substitute 0 there, the answer is negative 1 over h squared. Take a look at this next example. You have a limit as y approaches 0 of this expression over y. As you substitute this 0 into y in the numerator, you get 3x cubed minus 3x cubed. So that's a 0 and a 0 as well at the bottom. So the limit of the numerator and the denominators are both 0. We simply need to find y on top that you can cancel with the y at the bottom, so we can solve the limit. And to be able to do that, you have to notice immediately that both these terms here in the numerator contains a 3. We can factor it out, leaving a difference of 2 cubed, and applying the factoring for difference of 2 cubed. Refer to your factoring video. Then u minus v, or u cubed minus v cubed, is u minus v times u squared plus uv plus v squared. So this is the factor, and simplifying, this is x minus x, you'll get the y. You cancel the y here, and you've got the negative sign has been put outside here, so this one, and as you substitute your y, you get negative 9x squared. We now go to one-sided limits. Remember, in our introduction for limits, we say the limit of the function as x approaches a is equal to L, and we show you that x is approaching a from the left and from the right. Actually, we define as well one-sided limits. The one that you get as x approaches a, so as x approaches a certain number from the right, we call that the right-hand limit, and from the left-hand limit. So as you can see here, though the limit of the function f of x, this piecewise function, is undefined because the right-hand and the left-hand limits are not equal, but each of the one-sided limits exist. The limit of this f of x as x approaches 2 from the right is equal to 2, while the left-hand limit as x approaches 2 from the left is equal to 5. In this function, as you can see, this is 1 here, so if we observe, the left-hand limit of this function here is equal to 4, while the right-hand limit is equal to 1. Okay? So we have this notation for one-sided limits. The limit of f of x as x approaches a from the right is equal to L, right hand. Left hand, so you observe that difference. You've got a minus here and a plus on the right hand. Now, the limit theorems still holds for one-sided limits. Please remember that. Next, and this is very important, is that the limit of the function as x approaches a exists if and only these two limits, or the two one-sided limits, must be equal. They both exist and are equal. So consider the function, or consider the example here, the function absolute value of x over x as x approaches 0 from the right. Be careful with absolute values. Remember the definition of the absolute values. Absolute value of x is equal to x if x is positive, and the absolute value of x is negative x if x is negative. You can remember that when we say that the absolute value of 5 is 5 and the absolute value of negative 5 is also equal to 5. So if your x is negative, you need to multiply a negative to that number to make it positive, because in early mathematics we understand that the absolute value of a number, we take the positive value of it all the time. Okay, so actually this is the definition of the absolute value. The absolute value of x is positive x if x is greater than 0, and negative x if x is less than 0. Now, x is moving to 0, or x is approaching 0 from the right. That means to say the values that x takes to approach 0 cannot be negative. They are all positive. If x is moving to 0 or approaching 0 from the right, it must come from 1, then less than 1, until it goes to 0. So in this case, x approaches 0 from the right, x must be greater than 0. So we take the positive value for x. So we just substitute x here, the positive value, and then x divided by x is 1, so the limit is equal to 1. On the other hand, the limit of the function absolute value of x over x, as x approaches 0 from the left, since x is approaching 0 from the left now, then the values of x here as you approach 0 are negative. So we take x is less than 0, we take the negative value of x, substitute, hence the left-hand limit of this function as x approaches 0 is equal to negative 1. What can we say about the limit of this function as x approaches 0? The answer is it does not exist, because the left and the right limits are not equal. Take a look at this next example. You have the limit of the square root of 4 minus x squared over the square root of 6 minus 5x plus x squared. As you can see, if you substitute 2 here on both numerator and denominator, or you try to evaluate the limit of the numerator and the denominator, you'll get 0 for both. That means to say, you should remove the factors that makes the numerator and the denominator 0, and obviously that would be x minus 2. To be able to do that, then you need to recall again your knowledge in factoring. Factoring the numerator, that is 2 plus x, 2 minus x, and the denominator is 2 minus x and 3 minus x. We divide out these common factors here, leaving with this one, and substitute. You get square root of 4 over square root of 1, which is equal to 2. In the next example, you have the limit of 9 minus x squared over the square root of 3 plus 2x minus x squared. Still the same, as you evaluate the limit of the numerator and denominator, as you substitute 3 there, you'll get 0 over 0. So find all factors that gives you 3 minus x, or all x minus 3. Okay? And then you divide that out. So the factor of 9 minus x squared is 3 plus x times 3 minus x. Well, the factor of this radicand here is 3 minus x times 1 plus x. So we use the laws of radicals here so that we may be able to combine this 3 minus x. So this 3 minus x here, 3 minus x to the 1 and 3 minus x to the 1/2, we subtract the powers. So that's why you get a 3 plus x times the square root of 3 minus x. That comes from the 1 minus 1/2. So x to the 1/2, or square root of 3 minus x, leaving the square root of 1 plus x at the bottom. Now as you substitute 3 here, the denominator no longer 0. You get a 4 while the numerator is 0. So you've got a 0 as your answer. Here we go again. We have another absolute value. So what is the limit of this function as x approaches negative 2 from the left? Okay, now we need to recall again the definition of the absolute value of x plus 2. So as you can see here, we take the negative value of x plus 2 because x is approaching negative 2 from the left. Okay, x plus 2 is equal to the absolute value of x plus 2 is equal to x plus 2 when x plus 2 is greater than 0. It means to say x is greater than negative 2, and it is negative of x plus 2 when x plus 2 is less than 0, or x is less than negative 2. So here x is approaching negative 2 from the left, so x must be less than negative 2. So that's why we take the negative value of x plus 2, and then we find out that the numerator and the denominator, both limits at this point are 0 over 0. We remove the factors, that makes it 0, leaving 1. Substitute, you get a negative 4. For the next example, we have the limit of this function here. Observe that it is still 0 over 0, and because we have that remark, all the limit theorems are still applicable to one-sided limits, then we just simply remove the factors that makes this 0 over 0. Okay, and that is, those factors are x minus 2. So removing a common multiple x and then factoring this one, x squared minus x minus 2, there you get your x minus 2. And at the bottom, factoring the common multiple x squared and x minus 2. Dividing out these two, you will arrive at a function that is no longer has no longer a 0 as a limit for the denominator. Hence, you substitute and you get 3 over 2. And we also have an example here. Find the limit of this function f of x. It is a piecewise function as x approaches 1 from the right. Okay, so as x approaches 1, the definition of this function f of x here is that this is 2x squared whenever x is between 1 and negative 1, including negative 1, excluding 1, and 3 minus x when x is greater than or equal to 1 while less than 2. Okay, so when we say the limit of f of x as x approaches 1 from the right, then we just simply take a look at the domain of this function. Where is that 1 from the right of 1? So that could not be possible here because x here is less than 1. You can find this one here. Because x is approaching to 1 from the right, then x must be greater than 1. Okay? So that is why the limit of this function x, as x approaches 1 from the right, we should use the 3 minus x as the value for f of x. Okay? 1. And so that is equal to 2. When we say the limit of this function here, as x approaches 1 from the left, then it could not be possible here. Because when you approach when you approach 1 from the left, that means to say those values must be less than 1, and this is the interval where you get values of x that are less than 1. So you can approach 1 from the left here. So we use 2x squared as the value of your f of x, and you will still get 2. That means to say by the theorem that the limit of this f of x as x approaches 1 is equal to 2. Because both the left hand and the right hand limits exist and are equal. Okay, we have another piecewise function, g of x, given by this, x squared minus 6, with this condition, negative 5 when negative 1 is less than or equal to x, which is less than or equal to 10, and x minus 5 when this is the domain. So find the limit of g of x as x approaches negative 1 from the right. This is easy to solve. All you have to do is find the domain here, these 3 domains, find the 3 domains that satisfies this. When can you approach x, or when can you approach negative 1 from the right? The only domain in which x approaches negative 1 from the right, that is only possible when you have this one. As you can see here, x is greater than or equal to negative 1. So by this, you can approach negative 1 from the right of negative 1. That is why you substitute g of x by negative 5 here. And the answer is negative 5. For number 2, the limit of g of x as x approaches, this should be negative 1 as well. this should be negative 1, and this should be negative 1, because we don't have any 1 here in our domain. So we approach negative 1 from the left. So the only way we do that is when you have this condition. You can approach x, you can approach negative 1, x can approach negative 1 from the left. So we use x squared minus 6, and you find out that when you substitute, this should be negative 1. So negative 1 squared is 1, that is negative 5. Both the left and the right exist. That means to say that this limit g of x as x approaches negative 1 also exists and must be equal to this 2. Okay, must be equal to negative 5. Alright, we now go to infinite limits. What is infinite limits? Okay, take a look at this example. Oh, we have here a statement: the limit of the function 1 over x squared as x approaches 0 does not exist. And if you take a look at this table, as x approaches 0, first in this table, so as you can see, positive and negative, so you're approaching 0 both from the left and the right of 0. They have the same answer. Yes, because you have an x squared here. Whether it's positive or negative, you get a positive answer. You notice that the value, as you substitute it here, you can try that in your calculator, becomes very, very large. And as it gets closer and closer to 0, it becomes very, very large. That is also that can also be seen in the graph here. As you approach 0, the left hand limit, as you can see, is asymptotic to this y-axis, and as well as there. So as x approaches 0 both from left to right, we say that here, that's why it is a case of infinite limits, because the limit here is actually positive infinity. Okay, and since positive infinity is not a real number, we also say it does not exist. But in this topic, if limits are like that, it does not exist, we still describe whether the limit goes upward without bound or goes downward without bound. Okay, so whether it would be positive or negative infinity. So that is what infinite limits is all about. Limits whose answers would be positive or negative infinity. Take a look at this illustration. As x approaches 1, this function here should be asymptotic to this. So the answer here should be the limit of this function as x approaches 1 is equal to positive infinity. In this illustration, I think I generated this equation because I could not find a picture that goes to negative infinity, whose limit goes to negative infinity. You can see my picture here, and I'm opening a lot of tabs here. But well, you have, that's 10:39 a.m. Okay, so you have a function. I inputted a limit, the function 2 minus the fraction 1 over 1 minus x squared, and this is the result. It is actually asymptotic to 1. So that means to say the limit of this function as x approaches 1 is negative infinity. This is an asymptote here. You can verify that as well here because it is undefined when x is equal to 1. Here is the formal definition of infinite limits. So you can immediately look at this equation here. The limit of f of x as x approaches a equals positive infinity. What does it mean? It means f of x increases without bound as x approaches a. Similarly, we have the limit of f of x equals negative infinity, means f of x decreases without bound as x approaches a. We have this very important theorem. If r is a positive integer, then the limit of 1 over x to the r as x approaches 0 from the right is positive infinity, and the limit of 1 over x to the r as x approaches 0 from the left. That means to say you'll be considering negative values here. So you get negative infinity if r is odd, and positive infinity if r is even. That is because you're considering a odd numbers here. I'm sorry, negative numbers. So negative, when it is odd, for example, negative times negative times negative, you consider negative, and when it is even, you'll get positive numbers. We also have this theorem. If you have the limit of a quotient here, this is the case where you have the limit of the denominator is 0, but the limit of the numerator is non-zero. See, you have the limit of g of x equals 0, while the limit of f of x is a constant not equal to 0. Then you have 4 cases. If the limit of the case 1 and 2 means that the limit of the numerator is positive, and for number 1, if g of x approaches 0 through positive values of g of x, the limit is positive infinity. C greater than 0 and g of x approaches 0 through negative values of g of x, then the limit of this quotient is negative infinity. Then number 3 and 4, if the limit of the numerators are both negative. So for number 3, negative on top, and then g of x approaches 0 through positive values of g of x, negative infinity. Negative on top and positive, and g of x approaches 0 through negative values, then it is positive infinity. This is easy to memorize. You can do it in this way. You have positive, positive, that's positive infinity, positive, negative, that's negative infinity. So just like multiplication, negative, positive, negative infinity, and negative, negative, you get a positive infinity. We also have another theorem here, the limit of a sum, in which one of the term here has a positive infinity limit. So if limit of f of x is positive infinity and g of x is a constant or a real number, then the limit of the sum is just equal to positive infinity. It tells us that in a sum, the constant, the limit of this g of x, or if one of the limit is constant, it will never affect the sense of the infinity. Okay, so positive infinity, it could not affect the sense of this infinity here. It will also be positive infinity. And for the product, for a sum, the constant will not affect the infinity, but let us see with the product. If c is positive, so you've got a product f of x and g of x, find out the limit of this product here. When the limit of f of x is positive infinity, well, the limit of g of x is a constant. When the limit of g of x is positive and positive infinity here, you get a positive infinity. But you have a positive infinity and you've got a negative constant, the limit of the product is negative infinity. So it's somewhat like this, the limit of g of x really affects the sense of the answer. Okay, positive, positive, it's positive infinity. You've got a positive infinity for f of x here, but then you have a negative constant. So when it comes to product, the sense of the infinity has been changed to negative. And a similar principle, in similar fashion, you have a negative here, a negative and a positive, that's negative, and a negative and a negative infinity, that's a positive infinity. Still, the constant is affecting the sense of the infinity. Okay, let us consider the example. Example 1.19, number 1. You have the limit of the fraction 4 over the absolute value of x minus 4 as x approaches 4 from the right. So we have an absolute value and we have a one-sided limit, so we need to choose the appropriate value for this x minus 4 here. Now you have to recall that the value here, since x is approaching 4 from the right, we replace this absolute value by x minus 4. The other value there is negative of x minus 4. Had it been negative here or from the left, we use that. But in this case, we use x minus 4. So the limit of 4 over x minus 4 as x approaches 4 from the right. If we substitute the value 4 here in x, you'll get a 0 denominator and a non-zero numerator. The numerator, the limit of the numerator is positive, while x while x minus 4, so you have, since 4 is greater than 0, so 4 is the limit of the numerator is positive, and x minus 4 approaches 0 through positive values. What do you mean by that? When when x is approaching 4 from the right, take note, you can have 4.3. 4.3 is at the right of 4. Okay? 4.3 minus 4 is 0.3. That's positive. 4.2 minus 4 is 0.2. 4.1, that is 0.1. So actually, x minus 4, as x approaches 4 from the right, your x minus 4 approaches 0 through positive values. Because when this is, you have 4.3, 4.2, 4.1. When this is 4, this becomes 0. But you approach 0 through positive values. By the theorem, positive and positive, the limit here is positive infinity. Here we have a difference of fractions. Now you might observe that this is 0 here and this is 0 as well here. Well, to solve this, we take the LCD so that we will just be considering one fraction. So we take the LCD of these two fractions here. You have now one fraction, and upon substitution you get a 0 denominator and a non-zero numerator. So the limit of the numerator is of course -1, which is negative, okay, less than 0, and the denominator, as x approaches 0 from the right, so you will consider 0.3, 0.2, 0.1, 0. You approach 0, the x squared approaches 0 through positive values, then you have a negative, positive, you have a negative infinity. Another example would be the limit of 4 over t minus 1 cubed as t approaches 1 from the right. This is exercise 1.19, number 5. Now you have, if you substitute, you get 0 denominator immediately, and you have a non-zero numerator, positive. But take a look at t minus 1. As t approaches 1 from the right, also positive values. You might consider 1.1 or 1.3, 1.2, 1.1. You'll get positive values here. So positive, positive, the answer is positive infinity. And last, second to the last, I think, you have two fractions again. Now when dealing with two fractions, to make it a lot easier, you consider here you have two fractions, but the limit of the other one is must be infinity, while the other one is not. See, as you can see, the limit of x plus 4 over x minus 4 as x approaches 3 from the right is -7. That's 3 minus 4, and 3 plus 4 here, yes, that's a -7, negative. While the limit of 5 over x minus 3 squared is positive infinity. Why? You have a positive on top, 3 approaches, or x approaches 3 from the right. That means you can consider 3.3, 3.2, 3.1, minus 3. Those are positive numbers, so positive infinity. Now this is a limit of a sum, and remember, the constant cannot change the sense of the infinity here, so the answer is positive infinity. The next topic is limits at infinity. What do we mean by this? Okay, this is the formal definition of the limits at infinity. As you can see, it differs from infinite limits. Infinite limits is limits, or are limits whose answers are either infinity or positive infinity or negative infinity, while limits at infinity is, you can find the infinity here. You replace a by your positive or negative infinity, and that's limits at infinity. What do you mean by this? So you have here the limit of f of x as x approaches positive infinity equals L, while at the bottom you've got a limit of f of x as x approaches negative infinity equals L. Now the meaning of this for positive infinity is the limit of f of x as x increases without bound is L. The limit of f of x as x decreases when you have a negative infinity without bound is L. Okay, I decided to use a parabola. Take a look at this arrow here. What do you think will happen? What do you think is the limit of this function as x approaches infinity. So as you make x very, very large, this guy here goes up without bound. So actually this is the case where you can say we have an infinite limits at infinity. The answer here is infinity. Well, you might say, oh, maybe all the answers here are infinity because we are approaching x to infinity. We're making x very, very large. Now take a look at an example. Here, consider this function, and this function we have an asymptote here, and this function is asymptotic to this line, horizontal line y equals 4. So what do you think is the limit of this function as x goes to infinity, positive infinity? So you can see, no matter how you make x very, very large, this function f of x here tends to approach 4. It will never cross 4 somewhere here. So this is an example where the answer is not a in infinity. In fact, the answer for this function, if this is the case where it is asymptotic here and it approaches there, the limit of this function as x approaches positive infinity is equal to 4. We consider these two theorems. If r is a positive integer, then the limit of 1 over x to the r equals 0 as x approaches positive infinity, and as well as negative infinity, it is equal to 0. This is very, very helpful when we solve problems that involves limits at infinity. Take a look at this example. We have the limit of 3x to the fourth minus 7x squared plus 2 over 2x to the 4 plus 1 as x approaches negative infinity. The technique is this. Find out immediately the degree of the polynomial for the numerator and the denominator. Whichever is highest, you use that variable with that degree and divide both numerators and denominator by it. In this case, x to the fourth. So you have an x to the fourth here. We divide immediately numerator and denominator by x to the 4. Well, it's just like simply multiplying by 1. This is 1 over x to the 4 divided by 1 over x to the 4. That is just equal to 1. We're not changing actually this. We're not changing the value, only its form. So what will happen? This becomes the limit x to the 4 divided by x minus 4. X to the 4 is 3. This one, x squared over x to the 4 is over x squared, and this is 2 over x to the 4th. X to the 4th cancelled, so you have 2 and 1 over x to the 4th. Now, with the previous theorems, this one is just equal to 7 times 1 over x squared. Now, the limit of 1 over x to the r, whether it could be x approaching to positive to negative infinity, is 0. So the limit here is 0. 7 times 0 or 0. The limit here as well. This is 2 times 1 over x to the 4. 1 over x to the 4, the limit there is 0. So this is 0, this is 0, as well as this, 0. So the answer, what's left, is 3 over 2. The answer is 3/2. So that is how you apply the previous theorems in simplifying or in solving limits at infinity. Okay, so I also included here, what if y approaches negative infinity in the previous example? So take a look. You have to divide square root of y squared here on top, but then in denominator you need to choose the appropriate value for y. Okay, the appropriate value here is negative y. Okay, so square root of y squared and negative y are the same or just equal when y approaches negative infinity. So we're just simply multiplying this expression by 1 over square root of y squared over 1 over negative y, which is equal to 1 when y approaches negative infinity. Okay, so we have here, just like in the previous example, we simplify, radicals join into 1, and then you get negative 2 minus 1 over y. This is 0. The limit here is 0, negative 1/2. Example 1.23, number 5. You've got the limit as t approaches positive infinity of this fraction here. This is cube root, not a square root, so you don't need to worry about the absolute value. Just determine the degree. Of course, this is t cube and a cube here, so that's just t to the 1. So I'll divide a t here in the denominator while I divide cube root of t cube. So this is just simply multiplying 1 over cube root of t cube over 1 over t. This 2 divides out. They are the same as t approaches positive infinity. Okay, so t cube root of t cube is just equal to t. Okay, now the numerator, since they have the same index, by the loss of radical we can combine them and simplify in this form. T cube divided by t cube is 8, so cancel t cube. Then t squared divided by t cube, that's 1 over t. This is y minus 1 over t cube, and the denominator becomes 1 over t, so you have this one, and minus 5. Okay, but as you can see, when we try to evaluate the limit of the denominator and numerator, limit penetrates this radical here, and the limits of these fractions here is 0. This one as well is 0, so you've got a cube root of 8 over negative 5, or simply negative 2 over 5. Okay, this is second to the last example, I believe, for limits at infinity. We've got a limit of this binomial here, square root of x squared plus x minus x, as x approaches positive infinity. This is strange because we don't have a numerator. We don't have a denominator here. So the way we do this is, I think you have an idea now, binomial with a square root, we multiply this by its conjugate, both from the denominator and the numerator. By the way, the denominator here is equal to 1, so completing the difference of two squares in the numerator, so we get this, removing the square root, squaring the v. Okay, and then you have this denominator now. Okay, now x squared minus x squared is 0, so you have the limit of x over the square root of x squared plus x. Okay, now we recall again by the definition of absolute value of a number. So this case actually is similar to the previous examples. We've got a square root of x squared, which is the definition of an absolute value. So you have square root of x squared is equal to either x or negative x if you have a negative x if x is less than 0, and x if x is greater than 0. But since x is approaching positive infinity, then x is approaching to, or then x must be greater than 0. So we use the positive. Here we divide the denominator by square root of x squared, while we divide the numerator by x. Okay, this x and square root of x squared are equal when x is approaching to positive infinity. Alright, the numerator becomes 1, while simplifying the denominator, as you can see, we break down the fraction here with the square roots and the numerator without square root here. Alright, now simplifying, this is just equal to 1 because the square root of x squared when x approaches to positive infinity, this is absolute value. We just substitute this with x, just like the same reason here. Okay, while this radical here can be simplified as 1 plus 1 over x. So you've got the limit of 1 over the square root of the quantity 1 over x plus 1. And this is a constant. The limit of a constant is a constant. The limit of a constant, the limit of a constant, this is the limit here is 0. So you've got 1/2. And finally, we've got the limit of 2x minus x squared over 3x plus 5 as x approaches positive infinity. The degree that is the highest for numerator and denominator is x squared. So we divide both numerators and denominators by x squared immediately, obtaining this 2 over x minus 1. So you simplify that one, and then 3 over x plus 5 over x squared. Notice that the limit of the numerator here in this part is negative, okay, but the limit of the denominator is 0. Okay, you have 0 here plus a 0. Remember, you have a negative, a constant, non-zero, and a 0 denominator. What case is this? This is actually a case of infinite limits. So you have to recall, we have 4 cases there. You have a negative numerator, so we have to evaluate whether this denominator approaches to 0 through what values as x approaches positive infinity. So we've got here, we stated that already, the limit of 2 over x minus 1 as x approaches infinity, this is 0. So negative 1, which is negative, okay, we have to remember that. So we have case 3 and case 4. And then evaluate this. X grows larger, so meaning to say this becomes 10, 100, 1000, and so on, as well as this, much bigger. So when we simplify that, it's a very small number, but these will be always positive, right? As x approaches positive infinity. This gets smaller and smaller. This 2 sum here becomes very, very small, but these are positive. It can never be negative as x approaches positive infinity. So you've got a negative numerator, negative, positive, the negative infinity. Okay, the next topic is continuity of a function. This is the definition of a function that is continuous at the number a. It is continuous at the number a if the following 3 conditions are satisfied. You have f of a exist. Second, the limit of f of x exist as x approaches a, and the limit of f of x as x approaches a must be equal to f of a. These 3 are the conditions for f, the function f, to be continuous at the number a. If one of the conditions fail to hold, then the function f is discontinuous at a. Now, if it is discontinuous at a, there are 2 types of discontinuity. One is removable, that happens when the limit exists, but discontinuous, and the other one is essential, when the limit does not exist. And if it is a removable discontinuity, we can just easily redefine the function to make it continuous. Take a look at this example. We have determined if the given function is continuous at the indicated number a. Your a here is equal to 1. And if it is discontinuous, we have to determine with what type. Is it removable or essential? So we have a piecewise function here, the fraction x minus 1 over absolute value of x minus 1 if x is not equal to 1. And we've got a 0 if x equals 1. So remember the 3 conditions. Number 1, find f of a or f of 1. So first, where is x equal to 1 here? Obviously this one. So f of x equals 0, or f of 1 is equal to 0. The second condition says that the limit of f of x must exist. Okay, so recall that when we try to solve for the existence of a limit, we can do that by simply solving for the left-hand limit and the right-hand limit. If those two are the same, both exist and are the same, then our limit exists and is equal to that number. Okay, but we have here an absolute value of a number, or an absolute value of x minus 1. So let's recall that the absolute value of x minus 1 is positive x minus 1 if x is greater than 1, and the absolute value of x minus 1 is the negative of x minus 1 if x is less than 1. Okay, so we solve for the right-hand limit. Right-hand limit here, x approaches 1 from the right. That's why we use 1 from the right. This is x is greater than 1. So we use the positive x minus 1. And just cancel. That is equal to 1, the limit of a constant 1. So the right-hand limit is equal to 1. Let us take a look at the left-hand limit. Now the left-hand limit, we simply substitute the absolute value by negative x minus 1 because x approaches 1 from the left of 1. Okay, and we get negative 1. Unfortunately, the limit, the left and the right does not coincide, or they're not the same. So we say the limit does not exist. And so since the limit does not exist, we have an essential discontinuity. In the next example, we still determine whether the given function g is continuous at a equals 4. So similarly, we find out first g of 4, g of a. G of 4, this is x equals 4, so g of 4 is 7. Okay. Next, we solve for the left and the right hand limit. So the limit of the limit of this function g of x as x approaches 4 from the left of 4. So meaning to say, now here, the meaning of x not equal to 4 is there are two cases here. You can have, if they are not equal, then x should be either greater than or less than 4. So that is why for the left hand, which is x is less than 4, you got this. For the right hand, x is greater than 4, you still got this. And that is why in our solution, we just combined it. We just evaluate it immediately because the left and the right uses the same fraction or the same value for g of x. So we immediately solve as x approaches 4. Take note that we have a 0 denominator here, 0 limit, as well as on top. So we do factoring to remove the x minus 4, and we get a limit of x plus 3 as x approaches 4, which is equal to 7. Now, the limit is 7, which is equal to g of a, and that is condition number 3. Condition number 1 exists, condition number 2, the limit exists, and condition number 3, the limit of this function g of x as x approaches to a must be equal to g of a. In this case, we've got both 7, so we say that g is continuous at a equals 4. Okay, we also have this example. Let us determine if this function is continuous at a equals 0. We have an f of x equals cube root of x plus 1 minus 1 over x. In this problem, I believe that if you have watched our video, uploaded video, in which is entitled Rationalizing Denominators, then you'll be able to solve this one. Okay? Using special products s cubed minus t cubed, which is s minus t times s squared plus st plus t squared, and considering x not equal to 0, we find that. So this is how we simplify f of x. Because notice that at x equals 0, you'll get a 0 over 0, right? So we need to find the value there. Okay, so what we do is the technique in rationalizing denominators. This is the binomial we multiply it with the appropriate or the suitable trinomial. This is your u minus v, so we multiply it by the u squared plus uv, which is this one times 1, plus v squared, which is 1 squared, which is just simply equal to 1. With this, the binomial and the trinomial, in that u minus v, u squared plus uv plus v squared, you'll get a u cubed minus v cubed. Eliminating these cube roots here, thus finding the value that makes the numerator and the denominator 0. Okay, so as you can see here, oh, I write it directly. Okay, let me explain. This becomes cube root of x plus 1 cube, which is x plus 1 minus 1 cube. So x plus 1 minus 1 is equal to x. Alright? And then you still have your x here times this term here. We cancel x, so we have a 1 over this one. Now the limit of this function f of x, this one here, as you substitute 0, it's no longer 0 over 0. So, in fact, it is equal to 1/3. Okay? Now, from the definition, f of 0 is not defined. See, you only have an f of x there. So, f of 0 is not defined because when you substitute 0 there, it makes it undefined. You have a 0 denominator. Therefore, what do you think? F is... yes, discontinuous at 0. And since the limit exists, we have a removable discontinuity, and to simply make it continuous, obviously a while ago this is just the given, right? So we just make it piecewise, add a condition that when x equals 0, it is equal to 1/3, which is the result of the limit. So that your f of 0 becomes 1/3, which is equal to the limit, so it is now continuous. Let's now go to the limits involving sine and cosine. We have these two helpful theorems. The limit of cosine x minus 1 over x is equal to 0. This is not cosine of x, cosine of quantity x minus 1. No, it is quantity cosine x and then minus 1 over x, which is equal to 0. And the limit of sine x over x equals 1. Let us test these two theorems with the following examples. Example number 1, the limit of sine 7x over sine 2x as x approaches 0. So take note that the limit of sine x over x as x approaches 0 is equal to 1. Okay, but how do we do this? We simplify this by, take a look at how it is being simplified. So it's like we construct the sine x over x. So we have a 7x here, so we divide a 7x at the bottom, but we also multiply a 7 here so that the 7 gets cancelled. We also have a sine 2x here. We divide 2x here so that this will be completed, and we can apply the theorem. Multiply by 2 so that this 2 here will be cancelled, and your x here divides out. So actually it's just equal to 1. It's like you're multiplying this whole thing by 1. I repeat, this is sine of 7x. To be able to apply the theorem, we divide this by 7x and we divide this by 2x, so the x gets cancelled here. Now our problem is the 7 over 2, so actually we just multiply 7 here to cancel that, and we multiply a 2 here to cancel that. Alright, so it's like changing its form but not its value. Okay, so note that x approaches 0 if and only if 7x approaches 0. If x approaches 0, what happens to 7x? This gets smaller, this would also get smaller, and eventually when this is x is equal to 0, 7 times 0 is also 0. Also, x approaches 0 if and only if 2x approaches 0. So similarly, we've got this one, and this is our theorem. Okay, we actually distribute the limit or solve the limit on top the numerator and the denominator now. So the limit of 7x over 7x, as 7x approaches 0, is equal to 1. Okay? So this is, in the theorem, this is x, and this is x. So satisfied. Okay? They're all the same. As well as here. At this point, you cannot yet apply the theorem because this is 2x, but this is x. So, but you can argue, we have argued that when x is getting smaller to 0, your 2x as well is approaching to 0. So you can just replace it by 2x. So 2x, 2x, and 2x. The limit of this is equal to 1. Okay? The limit of the denominator is non-zero, so we can just simply distribute the limits. So we have the limit of sine 7x over 2x is just this one. Okay, which is 7 over 2 times 1 times 1, 7 over 2. Okay, you have evaluate the limit of 1 minus cosine x over sine x as x approaches 0. So in here, your problem is that you don't have an x, right? You can recall that the limit involving cosine and sine, you have 1 minus cosine over x and a sine x over x. So I think this is very easy to see. You just divide both numerator and denominator by x and you will get to apply, or you can now apply the theorem. See? You divide by x, you see this, and you see that. So since the limit of the numerator now is 0 and the denominator is 1, 0 over 1, it is equal to 0. Okay, I think this is the final example for limits involving sine and cosine. We've got a limit of 3x times cotangent 3x. This is exercise 1.33 number 3. The problem for this is that we don't have an identity or a theorem for cotangent. So we need to recall a little bit of trigonometry here. Notice that cotangent 3x, or remember that cotangent 3x is just the same as cosine 3x over sine 3x. Okay, so we have now this limit as written as this. The trick is this. We group 3x and sine 3x and cosine 3x here. And another trick that is applied here to be able to solve this problem is rewriting 3x over sine 3x. We write 3x over sine 3x because we don't have a theorem for this. We have a theorem for a sine x over a variable, right? So the way we solve this is we rewrite this in such a way that it becomes that the sign is on top. So we write this 3x over sine 3x as 1 over sine 3x over 3x. Are they equal? Yes, they are equal. Just like, for example, you say 5 is equal to 1 over 5. Okay? So I will write this as 1 over 3x sine 3x, and then you flip the 1 over 3x sine 3x into sine 3x over 3x. Well, you might also do dividing this. 1 divided by this, so get the reciprocal of the denominator or the divisor, so it becomes 3x over sine 3x. So this is how we are able to obtain this one. Okay, now take a look. You have distribute the limit because you can see the limit of 1 is here, constant is 1. The limit of sine 3x now over 3x, we cannot yet apply the law here or the theorem, but we argue that when x is approaching to 0, also 3x is getting smaller and is approaching to 0 as well. So by this time, you can say that the limit here is 1. The limit here is 1. The limit here is 1. How about the limit of cosine 3x? Recall that when you substitute, recall that cosine of 0 is equal to, yes, cosine of 0 is 1. So when you substitute x there by 0, you have a cosine 0 which is equal to 1. So you have 1 times 1 divided by 1. The limit of this function is equal to 1. Alright, thank you for listening, And up next will be discussion on derivatives. God bless you.